In every programmer's life, there comes a moment when a thought appears. What if I make my own game engine? For me as well, once while I was watching a sunset, I thought about game engines, Unreal, Unity, and then I said to myself, nah, I can make something cooler. But of course, making something even close to Unreal or Unity is almost impossible, especially for a solo developer. So my engine wouldn't be too big. Anyway, creating an engine is a great opportunity to learn something. I've started building my own game engine in C++ using OpenGL as the graphics API. Think of it as the basic toolkit. OpenGL takes care of the rendering, drawing shapes, handling textures, and basically everything that shows up on the screen. Every 3D game engine starts the same way, by drawing a single triangle. But why a triangle? Why not quads, or even circles? The answer is all about simplicity. Triangles have just 3 points, and by definition from school geometry, we know that any 3 unique points that don't lie on the same line always form a flat surface, a plane. That's a huge deal for your GPU. Drawing a flat triangle is easy, but a quad with 4 points? Quads can bend, twist, and break the flatness rule, and that's a total GPU nightmare. Triangles are flat, predictable, and easy to work with. That means you can map textures, calculate lighting, and do all the math without headaches. You can build any shape from triangles, quads, cubes, and complex models. But if you try the other way around, starting with quads, it just doesn't work. Back to programming. To draw a triangle in OpenGL, the first thing we need is its vertices, basically the points in space that make up the triangle. But here's the thing, we're drawing with the GPU. GPUs are super fast because they can draw many elements in a single call. The CPU? Not so much. It can only handle 1 element per call, which is really very slow. That means we need to send the triangle's coordinates to the GPU. OpenGL helps us with that. We create buffers and load our triangle's vertices into them. Just throwing vertices in there isn't enough. We also need to bind them so the GPU actually knows what to do with that data. Otherwise, it's just sitting there doing nothing. And to finally make this triangle show up on the screen, we need something special, a shader. Now, if you Google shader, the first thing you'll probably see is Minecraft shaders that add realistic shadows and lighting. But in reality, a shader is a tiny program that runs on the GPU and manipulates input data, in this case, our triangle vertices. Shaders let us add shadows, lighting, fog, explosions, and all the cool effects you see in modern games. Without shaders, your triangles would just sit there, boring and flat. In modern OpenGL, there are 2 core shaders you can't avoid, vertex and fragment. The vertex shader runs once for every vertex you send to the GPU. Its main job is to take the raw vertex data, positions, normals, texture coordinates, and push it through the rendering pipeline. In practice, that usually means multiplying the vertex position by the model, view, and projection matrices. The result of this step is that a 3D point from your scene ends up in the correct place on your 2D screen. You can also pass extra data down the pipeline from here. The fragment shader, on the other hand, runs once for every pixel covered by your triangle. Its main responsibility is to output the final color of that pixel. Here you can do all the fun stuff, lighting calculations, applying textures, procedural effects. Well then, let's actually add some super simple shaders to our code. And we finally get our very first triangle on the screen. Pretty cool, right? It might look simple, but this tiny triangle is literally the first building block of every single 3D game you've ever played. Also, to better understand how shaders work in the rendering pipeline, we can represent it with a simple diagram. First, we load data into the GPU, like vertex positions and colors. Then the vertex shader takes over, processing each vertex and transforming it as needed. After that, the fragment shader kicks in, deciding the color of each pixel. Finally, we call OpenGL's draw function, and voila! The GPU produces a frame on the screen. This exact sequence repeats for every frame, forming the visualization you see in your game or application. Okay, so right now we only have a single triangle. That's cool, but obviously not enough for a graphics engine. Let's step it up and draw a cube. And it's not that hard. All we need is to add more vertices into our buffer. Those will form the extra triangles that make up a cube. Once we enter the cube coordinates and look at the render, it doesn't really look like a cube. We just see a square. That's because we're staring directly at the front face. To actually see it in 3D, we need to rotate the cube and reveal its other sides. In computer graphics, we do this using basic transformations, moving vertices around, scaling, and rotating them. The standard way to apply all of these at once is with a model matrix. The model matrix translates an object from its local coordinates into the world coordinates. Local coordinates are defined in the object's own space, for example, as they come from a model file that we load into the scene. The model matrix is the result of multiplying three main matrices: translation, rotation, and scale. The rotation itself is not just one matrix, it's actually a combination of three rotation matrices, each responsible for rotation around one of the axes, x, y, and z. But don't worry, the computer can handle all this math for us. Since C++ doesn't have a built-in matrix type, we'll use the GLM library, which gives us all the matrix operations we need. We build a model matrix, send it into the vertex shader, and multiply it with each vertex coordinate. A vertex is just a point in 3D space, so mathematically we can think of it as a 3x1 vector. But here's the issue. Our transformation matrices are all 4x4, and for matrix multiplication, the dimensions have to match. This is exactly why we use homogeneous coordinates. We extend our 3D vector into a 4D vector by adding an extra component. That last one, the W component, makes it possible to represent translations and perspective using the same 4x4 matrix math. Without it, you couldn't combine rotation and movement in one step. And after all the transformations are applied, the GPU just divides everything back by W, bringing us into normal 3D space. Now, if we want our cube to rotate smoothly, we need proper animation. Simply adding a fixed rotation every frame won't work, because the speed will then depend on the frame rate. On a powerful computer, the cube would spin too fast, while on a slower one, it would barely move. This kind of bug actually appeared in some old games like Skyrim and Fallout 4. Their game logic was tied to FPS, so when the frame rate went up, for example, when looking at the ground with fewer objects to render, characters could move or animate faster than intended. Instead, we measure the time delta between frames. At the start and end of the loop, we get the current time, subtract them, and use that difference as input for the rotation. This way, the rotation speed stays consistent across all machines. After all this, we get cube rotation animation. But something still looks off. The closest side of the cube appears to be the same size as the farthest side. That's because we're using an orthographic projection. In orthographic projection, objects don't get smaller as they move farther away, unlike in real life. To fix this, we can add a perspective matrix to our vertex shader. GLM can help us calculate this matrix easily. Another cool idea is to add camera movement in the 3D scene. For this, we use another matrix, the view matrix, also handled with GLM. Explaining view and perspective matrices in detail is a whole topic on its own, maybe for another video. Finally, with all this matrix multiplication, we can get a really cool, fully 3D-looking cube. Another important part of a game engine is the object rendering system. And it's not really about graphics itself. It's more about making our code clean and manageable. For example, to render a single cube, right now we have to do a lot of extra work. First, we load the vertices to the GPU. Then, every time we want to draw it, we have to bind the buffer again. Imagine doing this for 100 objects in your scene. Your code gets messy really fast. On top of that, different objects need different shaders. Metal needs one shader, wood needs another. To simplify all this, we can use inheritance. Here's the structure I use in general. Object, an interface with two main methods. Render, to draw the object, and update to update it over time. Mesh, handles loading vertices to the GPU. Material mesh, adds material properties, like shaders, and later textures. The key point is that every object in the scene has render and update. This way, we can keep all objects in an array and draw or update them in a single loop. Plus, adding new objects is as simple as calling add object. No messy setup required. The next step in building our engine is adding textures to objects. As always with OpenGL, there's a bit of setup. We have to create a texture, bind its ID, and load an image from the file system. To make this easier, I wrote a simple texture class. It takes care of all the boilerplate, creating, binding, and loading. So when it's time to render, the class does all the heavy lifting for us. But textures also need coordinates. So along with vertex data, we now pass in texture coordinates to the buffer. That way, OpenGL knows how to map the image onto our mesh. And with that done, we can finally load textures and bring some beauty into the scene. As a first test, I loaded a box texture and applied it to a cube, and it already makes the scene look way better. After adding textures to our scene, the next step is loading 3D models. There are a lot of different file formats for 3D objects, and writing your own parser for all of them would be way too long and unnecessary. Luckily, we already have libraries that do this for us. One of the most popular is ASSIMP, the Open Asset Import Library. I decided to use ASIMP because it can load pretty much any format and even handle models that contain multiple objects. To manage this, I created a new model class. It stores an array of all the meshes that belong to the model, and it also has a draw function that simply goes through the array and renders everything. With this in place, adding complex 3D assets to the scene becomes really straightforward. And here's a funny illusion. The entire sky you see is actually just one huge sphere. We're basically standing inside it, and if we wanted, we could even look at it from the outside. Now let's add something that makes the scene look way more realistic: shadows. Right now, if we look at our objects, they feel flat, almost like cardboard cutouts. The solution is the Phong reflection model, which is made up of 3 parts. First, ambient lighting. This is a constant base color that makes sure objects are never completely black. Even in total darkness, you can still see them a little. Second, diffuse lighting. Here we need some math. Imagine a light source shining on a surface. The brightness depends on the angle between the light direction and the surface normal. The normal is just a vector perpendicular to the surface, and the dot product tells us how much light it receives. Third, specular reflection. This is the shiny highlight you see on metal or polished objects. It depends on the viewer's direction. We take the light direction, reflect it against the surface normal, and then measure the angle between that reflection and the viewer's eye. The smaller the angle, the stronger the highlight. And finally, we just add up all 3 components, ambient, diffuse, and specular, to get the final result. And that's it for now. At this point, the engine already has a solid foundation, and soon I'll be adding more features. If you enjoyed this video and want to see the progress, make sure to subscribe, hit the like button, and leave a comment with your ideas or questions. Thanks for watching.